In this video, we dive into the secrets of the real-time TEK Vario and wind calculations, how it is done, and what we can benefit from. Measuring the movement of air in 3D space is highly complex. Without it, you're left in a swirl of uncertainty, unsure which path to take. Thermals are nothing more than vertical wind, blending with horizontal airflow, shaped by terrain and updrafts. That's why we prefer to speak of air mass movements. As an active glider pilot, Dr. Heinrich Meyer, professor of electrical engineering, always wondered why no system existed capable of calculating the movement of air masses in real time. That idea became TEK. He contacted LXNav, and they agreed to collaborate by providing their hardware and sensor processing expertise. Together with his doctoral student, Dr. Peng Huang, the team implemented the algorithm and tested the entire complex software system. TEK is the result of successful technology transfer from a major research project funded by the German Research Foundation. First, I want to be clear on 2 points. A normal, uncompensated variometer measures the air pressure, and the pressure changes are displayed as climbing or sinking. If you pull the stick, you introduce a climb, which is true but not initiated by a thermal. A TEK variometer, a total energy compensated variometer, compensates for this. Electronic or mechanic compensation calculates the total energy. So if you climb and you decelerate, a typical pilot introduced thermal, the compensation subtracts this and displays better values. But if there is a horizontal wind gust, there is no chance of compensation. You get a wrong reading on your display. I want to be clear on a second point. Humans better think in two-dimensional space. This is why we like to distinguish between the horizontal wind, also known as windsock wind, and the vertical wind, also known as thermal lift. But we are in a 3D space, so in reality, the wind is a three-dimensional vector. Only we humble humans want to separate normal wind from vertical lift. Calculating wind direction with the help of the magnetic compass is highly susceptible to interference from uncompensatable electronic disturbance fields. In addition, the Earth's magnetic field model is inaccurate. There have been various attempts to use magnetic sensors too. They all failed, so we leave this approach alone. And what about differential GPS? Well, this is no ideal solution because of some drawbacks. We need 2 antennas, one on the external fuselage, and it is expensive. But what data do we have?
Here we go. CMC attitude.
Well, a whole bunch. GPS data, static and dynamic pressure, and the IMU, the inertial measurement unit. The IMU provides acceleration data along all 3 axes, and its gyroscopes supply additional information about changes in the aircraft's attitude angles, roll, pitch, and yaw. And we know the theoretical sink rate of our ship because we know the polar curve. Okay, with about 20 parameters, we can estimate the flight path on which the plane theoretically is moving. To our interest, GPS data says something different. Why? Yes, you guessed it. The wind, or better we call it three-dimensional air movement. You may say, perfect, let's calculate the difference between real path and theoretical path. The result is the wind. And here we go with the crux of the issue. Without compass, respectively directional data, it's impossible to calculate this. Luckily, non-linear mathematical optimization theory gives us a helping hand. The Kalman filtering helps to estimate the solution to this multidimensional equation. If we jump from one measurement to the next measurement in very small steps, there are solutions to equate the formula. Hawk calculates our flight path in real time. It compares the predicted path with the sensor data. And because this is done 100 times a second, and based on the assumption that the wind changes are not major within 1/100th of a second, our estimation is fairly accurate. Super, so far so good. But what about the vertical wind? Didn't I say life isn't that simple? Well, actually, it is. Every vector has a vertical component too. For the sake of our limited imagination, we split it into vertical and horizontal parts. Voila! The result is a real-time estimation of the air mass moving around us, neatly separated into its horizontal and vertical components. Okay, and how does all this help us? I am only interested in optimizing my climb rate. This is exactly what we can do with this data. We have to understand that the TEK Vario and the Hawk Vario are two different instruments. They are complementary and best used in a dual instrument. The TEK Vario tries to indicate the actual climb rate. The Hawk Vario indicates the air mass movement around us. Look at this graphics. The turquoise arrows is the climbing air mass. We subtract the black arrow, the polar sink rate. But in reality, our sink rate is much larger. Why? Well, because of plateau effect of modern profiles, large side slip angle, rain bugs, malfunctioning of the static or dynamic pressure system, incorrect polar data, e.g. wing loading. For best results, we optimize our flight path in a way that we minimize the sink and use maximum of the potential climb. The next section presents real flight data and video examples, comparing the Hawk variometer with the TEK variometer. This example demonstrates a false lift indication on the TEK variometer. The red needle shows a spike, while the blue Hawk needle remains steady. Here is another example of a fake thermal. This analysis shows the TEK variometer reacting falsely due to increasing wind, illustrated by the black arrow. This log nicely illustrates the approach from the Durance to Ceres, showing the typical increase in wind strength and westward shift with northerly flow in the Venturi between the bathtub and the Crête de Sels. It is truly fascinating to observe this phenomenon live on the instruments. In addition to providing valuable real-time information for approaching the correct ridge, it also offers an excellent opportunity to analyze and understand the complex airflow patterns in the mountains. The Hawk wind is displayed with a gray arrow for the average wind, a blue arrow for the real-time wind. If enabled, an additional yellow arrow points to the direction of better energy. This example shows the real-time capabilities. The first second's average and real-time wind are identical, but soon, within seconds, the wind turns to left, then right, and then left again. The last example, with 50 seconds video in flight, shows the real-time lift indication capabilities. More than 1 second before the TEK Vario, the blue needle indicates raising air. Then the TEK Vario follows. Right here, the Hawk shows rising air much earlier, up to 4+. It has to be mentioned that this algorithm is highly dependent on accurate sensor data, so this is why the instrument and its position in relation to the airplane's axis is very relevant. Without calibration, the instrument shows incorrect data. We have two aspects to the calibration. First, around the pitch and roll axes, this can be done with the aircraft in a level attitude on the ground. Second, around the yaw axis. This can be done in flight. And because this sensor data is relevant, we have a very nice positive side effect. We also get the artificial horizon as a side effect. Airliner feeling included.